Welcome to this class. Today we'll be looking at top NABTEB Physics past questions. So let's dive right into it. And the first question here says, explain the sources of surface tension in a liquid. Now, surface tension is the ability of a liquid to appear elastic such that any substance that is placed on it that has very little amount of weight will start floating on top of the liquid. So if I have a liquid like this in a beaker, for example, let's say I have a molecule of the liquid here. Let's say this is molecule A and this is molecule B. Now, on the molecule of the liquid, we have forces pulling it in all directions. But on molecule A here, we only have forces pulling it downwards. Now, why is this? Now, the molecule of this liquid that are close to the top of the liquid, to the surface of the liquid, appear not to be having forces that are pulling it upward. Unlike molecule B, where you have forces pulling it in all directions, in molecule A here, you only have forces that are pulling it downward. And because the forces are only pulling it downward, this molecule A here will tend to be having an elastic format on the surface, such that any substance that drop on the surface of this liquid will remain on top of the liquid. That's why you discover that when you put a glass of water and you left it standing after some time, if you pour dusty material such as sawdust or powder, you discover that the powder will remain on the surface of the water. And the reason is because this water has been left standing for some time. So the molecules at the top of the liquid are now appearing elastic. And this is as a result of the cohesive force between the molecules of the liquid. And that is what we talk about when we're talking about surface tension. Moving on to the next question, which is question number 1B. It says, why would a ship made of steel float in water, whereas steel sinks in water? Now, the reason why a ship made of steel will float in water is based on two principles. The first principle is the principle of buoyancy, that says that an object, especially a hollow object that is placed in water, will displace the amount of half the amount of its volume that it is immersed in the water. And that principle is also called the principle of flotation. That is why substances are able to float in water. Another reason why the ship will float in water is because of the differences in the density. So once a substance has lesser density than the density of water, that substance tends to float in water. Any substance that has a lesser density than the density of water will always float in water. Likewise, if water has a lesser density than the density of any other liquid, that water will float on the liquid. So a substance that has a lesser density than the liquid that it is placed on will always float on the liquid. So we discover that your ship, although very heavy, has a hollow cavity and has compressed air within the ship, such that the density of the ship is less than the density of water, and it is partially immersed in water, which causes buoyancy. Buoyancy is the pushing up of that particular ship when it is immersed in water. Hence, that ship can float in water. Then why does steel, for example, a steel rod, sink in water? The steel rod, for example, has a higher density and it does not have high buoyancy rate. So because of the fact that that steel rod has higher density, because looking at the steel rod, it does not have any hollow cavity. So immediately you insert it into the water, it is going to sink to the bottom of the water because it has higher density than the density of water. So that is why a ship made of steel will float on water, whereas a steel rod will sink. Now, moving on to the next question, which is question number 1C. It says, how would you determine the volume of an irregular shaped object? How would you determine the volume of an irregular shaped object? Now, the first thing you're going to do is to pour water into a cylinder. So you pour water into a cylinder and note the volume. Let's say this is a cylinder and you note the volume of that water. Let's say you pour it down to this place. You note the volume as V1. And then you insert the irregular shaped object into the water in the cylinder, and you note the new volume V2. So we have gotten the volume when the irregular shaped object was not placed in the cylinder, and the volume after the irregular shaped object was not placed in the cylinder, so that you can now easily get the volume of the cylinder by subtracting the new volume V2 from subtracting V1 from V2 to be the volume of the irregular shaped object. So it means that if you want to find the volume of an irregular shaped object, you have to first of all find the volume of water, for example, or a liquid that you have available by putting it inside a cylinder to measure its actual volume, and then you put the irregular shaped object into the liquid and measure the new volume and subtract these two volumes to get the volume of the irregular shaped object. Moving on to the next question. Question number 1, this is an amount of mercury of relative density 13.6. So we have the relative density of mercury here as 13.6. Then is put in U-tube. Kerosene of relative density, this is mercury. Then we have relative density of kerosene as 0.8. Is poured into one arm of the U-tube to reduce the height of the mercury in that arm by 1.5 centimeters. So we have the height of the mercury as 1.5 centimeters. So determine the height of the kerosene in the column. So if the height of the mercury is 1.5 centimeters, it means that the height of mercury in both arms is times 2, because we have mercury in both arms of this particular U-tube. So it means that what I'm going to be having is 3 centimeters. So we have to find the height of the kerosene, but we know that the relative density times the relative density of the kerosene times the height of the kerosene is equal to the relative density of the mercury times the height of the mercury. So this means that I'll be having 13.6 times 3 is equal to the height of the kerosene times the relative density, which is 0.8. So I'll have 13.6 times 3. So I'll divide both sides by 0.8 divided by 0.8. It means that the height of the kerosene will give me 51 centimeters. So it means that the height of the kerosene in the column is 51 centimeters. Moving on to the next question. Question number 2A says, state the meaning of the terms. Roman figure 1 says mechanical energy. Now, mechanical energy is the virtue of work done. The virtue of work done. The virtue of work done based on the position of a body. So the virtue of work done based on the position of a body. So, and it is divided into your kinetic energy and your potential energy, which means that your mechanical energy has to do with your kinetic energy and your potential energy. So it's the addition of your potential energy and your kinetic energy. So while your kinetic energy is the energy due to motion of a body, the energy possessed by a body that is in motion, while your potential energy is the energy possessed by a body at rest, is the energy possessed by a body at rest. So, And this here, the kinetic energy is half mv squared, while your potential energy is mgh, which means that your mechanical energy is equal to your half mv squared plus mgh, which is the same thing as saying that I have m open bracket half v squared plus gh. So this is your formula for your mechanical energy, because the what addition of your kinetic energy and your potential energy. While your potential energy is talking about energy at rest, your kinetic energy is talking about energy due to motion. Then moving on to the next question, which is Roman figure 2, says we should state the meaning of the term joule. Now, joule is the unit of energy, and it talks about the amount of force per meter. So what we're simply talking about here is your joule. 1 joule is simply saying that what you have done, what 1 Newton meters. So your 1 joule is equivalent to 1 Newton meter. Why is it 1 Newton meter? Because we know that what the work done is equal to what force times the distance. So while the distance is measured in meter, your force here is measured in Newton. So it's talking about what if you say 1 joule, you are simply telling them that what 1 Newton force does what 1 moves 1 meter. So if your 1 Newton force does the work of 1 meter, it means your work done will be what 1 joule or 1 Newton meter. So if I apply a force of 1 Newton and it causes an object to move a distance of 1 meter, it means that I've done 1 joule of work. So your joule is just a unit to measure the amount of work that is done. Moving on to the next question, number 2b. It says, how do you explain the rise in temperature of a bicycle pump during the action of pumping up the tire? So they're asking you that if you start using your bicycle pump to pump the tire of your bicycle, you realize that after some time that the bicycle pump will become hot. That what is responsible for that heat that is generated by this bicycle pump? Now, when you are pumping your tire using your bicycle pump, you realize that you are moving in and out. You are moving the bicycle pump, that piston-like part of the bicycle pump, you are moving it in and out. And in the process of moving it in and out, you are generating a frictional force. And frictional force is hereby converted to heat energy. It's just like rubbing your palms together. You discover that after some time, there is friction, and that friction is going to generate heat. That's when you're rubbing your palms together, you realize that your palms become hot. The same thing as when you're using your bicycle pump. So while you're using your bicycle pump, you realize that frictional force is being used, and as a result, heat will be generated. Hence, you discover that your bicycle pump will become hot after using it to pump your tires. Moving on to the next question. Question number 2c. It says, sketch a graph, not to scale, of volume temperature for the range between 100 degrees Celsius and minus 100 degrees Celsius of water. So what is this saying? So if I have my graph here, and I have, this is volume, and this is temperature. Here I have minus 10, minus 20. Let's say this is minus 20, minus 40, minus 60, minus 80, and minus 100. And here I have 20, 40, 60, 80, and 100. So from 0 degrees, this point is a point of 0 degrees. From 0 degrees, you realize that moving downward, your graph will be moving downward. It's a straight line graph from 0 degrees down to minus 100 degrees Celsius. So, but from 0 degrees down to about 4 degrees Celsius. Your graph will be moving downward here. Why? Because from 0 degrees to about 4 degrees Celsius, there is a constriction or there is an anomalous behavior of water. Water does not expand uniformly. It reduces from 0 degrees, from 0 to 4 degrees Celsius, water normally reduces in volume. So, but from 4 degrees Celsius, you discover that the water will start increasing upward, so that this graph will not look like this. So from your 4 degrees Celsius, there is a uniform increase in the volume of water. But from 0 degrees to 4 degrees Celsius, there is a reduction. That's why you discover that if you try to heat up ice block in a container, if the ice fills up the container at 0 degrees Celsius, when it completely melts from 0 degrees Celsius to about 4 degrees Celsius, you realize that the container is no more filled up with the water, because it has reduced as a result of moving from 0 degrees Celsius to about 4 degrees Celsius. But if you continue heating it till it gets to 100 degrees Celsius, you realize that it will expand even down to the point where it will burst open your container if the container is very small, that it can no longer contain it, or that the container does not expand uniformly with the expand in the water present in the container. Moving on to the next question. Question number 2D. Roman figure 1 says, describe how you would check the accuracy of the fixed point of a mercury thermometer. Now, in any thermometer, we have two fixed points. We have the upper fixed point and the lower fixed point. Now, if you have a mercury thermometer and you want to check the fixed point of the thermometer, all you have to do first, to check the lower fixed point of the thermometer, you take ice block, for example. Ice is usually at 0 degrees Celsius. Let's say I have a beaker and then I have a funnel. And then I have crumbs of ice in the funnel. So you put your crumbs of ice in the funnel, and then you take your thermometer and dip it into the crumbs of ice in the funnel. And you wait for some minutes to read the point on the mercury where it coincides with the 0 degrees Celsius. So the point where it coincides with the 0 degrees Celsius is your fixed point. Ordinarily, the fixed point ought to be at 0 degrees Celsius, and since the fixed point of this your mercury ought to be at 0 degrees Celsius, so you also check what was the height of the mercury within this thermometer at 0 degrees Celsius, and you note it. If it is higher than it ought to be, then it means that this thermometer is 40. So in order to check also the higher fixed point, so this is for checking the lower fixed point. Lower fixed point. So in order to check the higher fixed point of this thermometer, you take let's say you take a beaker of water and you put it on your tripod stand and you heat it. So I have flames here from, let's say, a Bunsen burner. So you heat it, but you do not put the thermometer into the water. You suspend the thermometer above the water, so that when steam is evaporated from this water that you are heating up, the temperature of the steam can be read using the thermometer. So when you start heating it up, you discover that steam will start escaping from this water, and when those steam is escaping from this water, they heat up this thermometer, and at that point you discover that the mercury inside the thermometer will rise. So you wait for some time and you check the point where it has risen to. The point where it has risen to is the higher fixed point of your mercury thermometer. And if it is higher than 760 millimeter mercury, it means that this particular mercury thermometer is also 40. So this is for checking the higher fixed point or the upper fixed point. the upper fixed point. And the one I drew earlier is for checking the lower fixed point of your mercury thermometer. Moving on to the next question, it says, remember we got 2, says, a compound strip of brass and iron is straight at room temperature. Give a label diagram to show its appearance when it is cooled. So when it is cooled, you discover that what? It will bend this way. When it is cooled, you have it this way. So you discover that what? Your iron will still be straight. So this is iron and this is brass. So when you heat it, when you cool it, you discover that what? In a bimetallic strip, this is a bimetallic strip. So in your bimetallic strip, you realize that what? When it is cooled, your brass will expand to a particular point. And at this point, it will be what? Bent. So it will be curved this way. But your iron will remain the same because at that point, there is very little changes in the temperature of the iron as it is cooled from your room temperature to about 0 degrees Celsius. So depending on the level of coolness, that will determine whether the iron will be completely straight or it will be slightly bent. So that is why you discover that what? In this bimetallic strip, the brass is bent, but the iron is just slightly bent when it is what? Cooled. Moving on to the next question, which is question number 2DII. It says, II, the option B of it, said, describe one use of such a strip. So we're still talking about the bimetallic strip. Now we can use your bimetallic strip as thermostats in your electric irons. You can use them also as thermostat in your gas ovens. You can also use them as fire alarm system. You can also use them in thermometers. So they said we should describe one of the use, and you can use them, like I said before, you can use them in what? Fire alarm. In your fire alarm system, you realize that you have what? Two elements that makes up the bimetallic strip in your fire alarm. We have what? Copper and we have iron. So when the bimetallic strip fire alarm system is placed in a room and that room is heated up, you realize that what? The copper will become what? Enlarged, will expand. So when the copper expands, it's going to hit the point where it is going to trigger the alarm. So whenever you have your fire alarm system, you realize that what? The copper is usually what? Heated up first before the iron. Hence what? It will easily trigger the alarm system when it gets to a predetermined temperature. So there's a temperature that is set that when it gets to this particular temperature, it means that there must be a fire within the room. So at that point, when it gets to that temperature, that copper would have got fully expanded and what? We hit that alarm system to alert everyone within the building that there's what? Fire in the building. So that is what? One of the use of the bimetallic strip thermometer. Moving on to the next question, which is question number 3. Question number 3A says, explain 2 applications of total internal reflection. Some of the applications of total internal reflections include the optic fibers. We have your totally reflecting prism. We have your binocular prism. And we have your periscope prism. We also have other applications of total internal reflection. So the question says we should explain 2. So we're going to explain your fiber optics and your total reflecting prism. Now, your fiber optics, when light is moving from a denser medium to a less dense medium and it strikes the medium at an angle greater than the critical angle, you realize that that particular light suffers what we call total internal reflection. Now, your fiber optics is a particle that is very flexible, and it is used to view objects that are in places where humans can generally not travel, or objects that are it's a very tiny particle of about 2 micrometer in diameter. So it is very, very tiny, and it is used to transfer light or transfer wave from one point to another, and it can also be used to capture the image of object at very small particles, at very far places where humans can generally not travel, like in deep sea. So if they want to go into the deep sea to explore, you can use your optic fibers, and they can also be used to transfer signals from one point to another. Now, another one that we have is your total reflective prism. Now, your total reflective prism is a right-angled isosceles triangle. What do I mean? So your total reflecting prism looks like this. So it is right angle, which means that this place is 90 degrees. So here is 90. And because it is isosceles, it means that this place will be 45, and here will also be 45 degrees. So if light is incidented on this, let's say I have a beam of light coming this way, and it is incidented, this light will travel this way, and then travel this way, and then it is reflected from the prism. So this is one of the applications of your total internal reflection, and this is what we call your total reflecting prism. And your total reflecting prism is a right-angled triangle prism. It's a triangular prism, but it is right-angled, and it is isosceles in nature, meaning that one of the angles is 90 degrees, while the other two angles are 45 degrees to each other. So these are the applications of your total internal reflection. Moving on to the next question, which is question number 3B. It says, describe and explain the action of a rear reflector on a bicycle. Now, your rear reflector on a bicycle is a red either glass or plastic material at the back of the bicycle. Now, that rear reflector of a bicycle is supposed to reflect the light that is incidented on it. So when rays of light are incidented on the rear reflector of a bicycle, the light are scattered, causing a diffuse reflection. So when the light are scattered, because the rear reflector on the bicycle is red in color, the red ray of light is scattered more than all the other rays of light within the spectrum. So the rear reflector of the bicycle is supposed to reflect the red ray of light more than the other part of the spectrum of light when light is incidented on the reflector. Moving on to the next question. Question number 3C says, give the relationship between the angle of rotation of a mirror and the angle of deflection of a reflected ray when the direction of the incident ray is constant. So when a ray of light is incidented on a surface and then it is reflected on a mirror, for example, and then it is rotated. So when you rotate the mirror, the angle of rotation, let the angle of rotation be theta. So if the angle of rotation is theta, it means that the angle of reflection will be equal to 2 theta. So when you rotate your mirror at an angle of theta, the the light that is incidented on it will be what? Reflected at an angle of 2 theta. And the angle between the incident and the reflected ray will be equal to 2 angle of incident plus your angle of reflection plus your angle of rotation in this case. So it means I'm having what? 2 times the angle of reflection of incident plus your angle of rotation. So this is the what? Relationship that exists between what? The angle of reflection and what? Your angle of incidence as well as your angle of rotation. But what is the angle of deflection? The angle of deflection is equals to 180 minus your angle or angle between your angle, the difference between your angle of reflection and your angle of incidence. So plus your theta. So this is your angle of deflection when what? Your mirror is rotated and light is incidented on it. Moving on to the next question. Question number 3D. It says, you are supplied with the converging lenses, focal length 50 centimeters. So we have a focal length of 50 centimeters. We have another focal length of 5 centimeters. And we have another focal length of 0.5 centimeters. Say, which would you use as Roman figure 1, the objective lens of a compound microscope? Now, looking at this, so looking at all of this focal length, if you want to use one as the objective lens of a compound microscope, we are going to use the one of what? 0.5. So this is for what? Roman figure 1. We're going to use 0.5 centimeter focal length converging lens as our what? Objective lens. And the reason is because of its what? Small aperture. It can use it for what? Small aperture. So because of its small aperture, that's why we're using what? 0.5 centimeter focal length lens. Then Roman figure 2 says, which will you use for the eyepiece of a compound microscope? We are going to use our what? 5 centimeter for what? The eyepiece. And the reason is because of its wide aperture. Wide aperture. So we are using it because of its what? Wide aperture. So when you are using it for your compound microscope, for your eyepiece, you have to what? Look through it. So the aperture has to be wide for you to be able to what? Look through it. Then the last part, which one are you going to use as a magnifying glass? So if you want to use it as a magnifying glass, we're using this third one as our magnifying glass. And the reasoning is so that what? The object can continue to be inside the focal length. So if the object is within the focal length, you'll be able to what? Magnify it better. So we are using our what? 50 centimeter converging lens as our what? Magnifying glass, so that what? The object will continue to be within the focal length. So we've come to the end of today's class. Don't forget to check other videos in our channel so that you'll be well tutored for your exams. Thank you.
Hi, I'm sure you enjoyed the content you just watched. To see more episodes as that, preparing you for your oncoming exams, smash the subscribe button on this channel right now and visit the playlist that we've made for you, covering over 50 type of different exams, including JAMB, WAEC, Cacao, NEET, IALT, and the likes like that. Also, in every video you watch, we have the link to our apps where you can download on Google Play Store and Apple Play Store and practice hundreds of past questions for free.